Okay, so picking up where we left off last time. So as I mentioned in the comments and in the announcement, a lot of this is going to be referencing the online notes because for the next couple chapters, a lot of the things being referenced are graphical things. So, for instance, the first thing we want to talk about in chapter 11 is image compression, or really not just this is not one of the things we're going to be talking about in chapter 11. This is literally the only thing we're going to be talking about in chapter 11's image compression. So this is going to be entirely graphical. It would be a waste of time for me to draw a bunch of these images up here when you have tons of really, really good examples in the online notes that goes over this. So I'm not going to do that. Chapter 12 as well is character recognition, which also relies on a lot of graphical things. I'm not going to reproduce that. When it comes to the computational bits, I'll put pen to paper, but other than that, I'm going to be reading and talking about the notes. So I encourage you to have a look at those and read along. So as I mentioned last time, chapter 11 is image compression. So the idea is I have this is not really how the chapter starts, but this is the goal. This is the idea. The idea is I have an image, and this image is, I'm thinking of generating or storing the data in this image pixel by pixel. And so there's some data that must be stored for each pixel that corresponds to, that is the data that's going to generate this image. Okay, so if I'm storing this or thinking about storing it pixel by pixel, then a couple of examples mentioned at the beginning of this chapter. So if you have a color image, so then you're viewing every color that's going to be generated in this image as a combination of RGB, right? So red, green, blue, and each of these RGB values has some integer value between 0 and 255. So this would give a total of, if you want to know the total amount of if you want to know the total amount of integers, rather the total amount of combinations of colors in this case, you would need to consider 256 possibilities for each slot of RGB. So that's 256 cube total possible combinations. So or 256 cube total colors. If you're thinking of a grayscale image, then similarly you could think of every single pixel as storing data on how black, white, or gray that pixel is. So you're viewing everything as spectrum between black and white. So if 0 indicates black, 255 indicates white, then some integer between 0 and 255 inclusive indicates some grayscale pixel. So pixel values 0 to 55 indicate either black or white, but everything in between is some scale of gray or some shade of gray. So another way of thinking about this, and this is actually what we're going to use, because it means that computationally we don't have to think about integer truncation or worrying about keeping everything integer valued, is to consider a grayscale image, except instead of assigning integers between 0 and 255, we assign real numbers between 0 and 1, where 0 is black and 1 is white. Okay, and so that's what we're going to do, is this last option. So immediately, there's example 11.1, page 4 of the notes in chapter 11. So it gives an example of an image consisting of no grayscale, only black and white. And so that image is it's a 4 by 6 grid of black and white squares. So each white space corresponds to a 1 in the matrix below it. Each black square is a 0 in the matrix below it. And so they have encoded that image as a 4 by 6 matrix. Okay, and the whole purpose of what we're going to do with this info is I have limited I have limited storage capacity, right? So I have limited ability to, I cannot store infinitely many images. And even storing finitely many images, I have storage restrictions. So I cannot store finitely many images if they're really, really huge. The idea is that I want to compress the data in some way. I want to make it smaller while still retaining something essential about the data, right? This is the whole idea of not just image compression, but file compression in general. Is the idea is to toss out any redundant or extraneous data if possible, or to toss out data that's not necessarily extra or not necessarily redundant, but data that is maybe not worth as much as some other data. So you can see where the singular value decomposition is going to come in here, because our main interpretation of it so far is that it told us something about how much, well, one of the things it told us was which columns of the matrix in question could be tossed out while still preserving some set percentage of variance of the matrix, right? So we could actually compute how much of the variance of the matrix in question was retained by tossing out some number of columns in the matrix. So that was one of the main purposes of this. So anyway, for instance, returning to the example I had mentioned from the notes. So this is example 11.1 in the notes. So in the notes, the SVD of this matrix is computed. And so when the SVD is computed, the singular values are found. So the largest one of those is 3.198. So we'll look at example 11.1 and 11.2. So the largest singular value in this case turns out to be 3.198. Okay, and so there's a list of 4 singular values there, and the suggestion is made to set the smallest singular value to 0 to create this matrix sigma prime, as we did before. And looking at sigma prime and our new A prime, right? So form sigma prime by setting, let me list the singular values out from this matrix. So S sub 2 is 1.678. S sub 3 is 1.235. And S sub 4 is 0.6576. Okay. And so form sigma prime by setting S sub 4 equal to 0. And compute A prime, which is U sigma prime V transpose. So this is done. In this example. And when this is done, you see that you get a matrix that has values that are not all strictly between 1 and 0. So note, values may not be strictly between 0 and 1. Okay. Even though A contained only zeros and ones. Okay. So you might imagine that the same thing is going to be true when you have a matrix so our matrix A was actually particularly simple because the matrix A that we started with in this example was nothing but zeros and ones. But You might start out with a matrix. If you have some generic grayscale image in this way that we've defined, your matrix is going to have real valued entries between 0 and 1. So it's also true that starting out with a matrix with real valued entries between 0 and 1, you don't always end up. When you toss out, say, if you set one or more of these singular values to be 0 and compute this A prime by computing this singular value decomposition product, except you've replaced your singular value matrix sigma with this sigma prime by setting whatever singular values you've chosen to be equal to 0. When you compute this thing, you're just not always going to get a matrix that has values between 0 and 1. So the question is what to do if that happens. So the notes mentions there's two possible approaches. So the first would be to renormalize the values between 0 and 1. But there's a reason not to do this. So as is noted in the notes, the reason not to do this is that what happens is since a value of 1 is supposed to be a completely white value, then if you had a value like 1.1, rescaling would interpret the first as not completely white, but rather slightly more gray, which is just not accurate with how you're interpreting these white pixels. And so instead, there's a second approach, which is just leave the values alone. And what I mean by leave them alone is treat everything that is strictly between 0 and 1, inclusive, just like we defined. So between 0 and 1, it's some scale of gray. If it's 0, it's black. If it's 1, it's white. And if it is greater than 1, it's also white. And if it's less than 0, if it's negative, then it's just also black. Okay. And so I should say here, to fix the issue of entries in A prime possibly being greater than 1 or strictly less than 0, we say that A sub ij less than 0 implies that entry, that pixel is black. A sub ij equals 0 is black. A sub ij is strictly between 0 and 1. That's some shade of gray. Right? Darker gray, obviously, as it's closer to 0. Lighter gray as it's closer to 1. A sub ij equals 1. This implies that it's white. And A sub ij strictly greater than 1 also implies white. So this is what we mean by leaving it alone. So these middle cases is what we were doing. Otherwise, having entries that are strictly less than 0 or strictly greater than 1, we just say that those are either black or white, respectively. And it turns out that this actually gives us a lot more accurate of an interpretation of what's going on here. So, example 11.3 is the first two examples, right, which are really a single example, taken, so applying this and singular value decomposition in general to example 1, we get some pretty pictures here. Like I said, I'm not going to redraw these. So this is on page 5 in the notes, so page 5, chapter 11. So what does this look like? So in the first image in this example, it says, so with this in mind, our previous example, preserving 3 singular values. So recall I had 4 total singular values, S sub 1, S sub 2, S sub 3, and S sub 4. I took the smallest one and set it equal to 0, so that I formed sigma prime by setting that fourth singular value equal to 0. Then I computed this a prime by computing my SVD product, except with this modified sigma prime instead. Okay, so when I do that, you can compute how much of the variance I preserve here. So it's already done in this example. So preserving three singular values, that is zeroing out S sub 4, that preserves 97.12% of the matrix data variance, would be along with the original. So it has an image here showing on the left the original image we started with, and on the right the image generated from our matrix A prime. So in this example, what's being shown is matrix A, or image associated to matrix A, and image associated to A prime, where S sub 4 was equal to 0. So here, this is, I should say, image associated to A, and image associated to A prime. And this A prime was setting S sub 4 equal to 0. Okay. And this, just from this act alone, I can compute the variance. So variance preserved in this case is 97.12%. So think of how you would compute the variance there. Okay. All right, so that is what is shown in the first image. And you can see that it's a pretty accurate rendering of the image you started with. There are many of the squares that match up seemingly perfectly, so a lot of the black squares remain completely black in the image associated to A prime. There are a lot of the white squares that remain completely white. But of course, some of the white squares become slightly grayer, and some of the black squares become a little lighter, so that they're also gray rather than black. Or they're slightly less black. You see some of them are still almost black, but they're noticeably lighter. Okay, so that's something that's noticeable. And that is preserving 97.12% of the variance. So in the next bit, maybe I'll put this on a new sheet. So again, this is example 11.3, and so this is the second bit that is A, and then the image associated to A prime, where I have set S sub 3 and S sub 4 equal to 0. And the variance preserved is 86.95%. Okay, so this is the second line in this set of images. So again, on the left-hand side, I have the image I started with. Okay, so it's just black and white squares. And on the right, now I have this image associated to A prime, where this A prime was formed by setting my singular values S sub 3, S sub 4 equal to 0, and finding U sigma prime V transpose. So I'm just going to use single prime. I'm not going to call this A double prime or anything. That's what I'm saying here. So if you look at that second line, this is certainly not as accurate as previously. So the compression that we did in the first case, and note this is compression because I am essentially saying that in order to generate the thing that I'm interested in coming from matrix A, which is that image, I am tossing out some columns and saying that I can generate that matrix with less data. Right? That's essentially what you're doing here. Okay. So so then looking at this second line, you see that, oh, well, this image is not quite as good. So some more squares that were totally white are now gray. In fact, looking at this, only a couple of the squares that were white in the original image remain completely white in the second image, in the compressed image. And same thing is true for the black squares. Only a few of the black squares that were black in the original remain black in this compressed image. This is certainly not quite as good. And then the last thing that is done is tossing out all singular values but one. And in that case, the variance preserved is 68.18%. So another way of saying that is that keeping only the first singular value and tossing out the rest for this matrix actually preserves 68% of the variance, which isn't too bad, but you see in terms of image compression, looking at this example, well, now everything is distorted. There's not a single square that is not distorted in some. Well, there's arguably two white squares that are okay here. Everything else is distorted, and likely if we were to actually, maybe my eyesight's not that good, but it looks like even those that I previously thought remained white don't. So it seems like every single square has changed a little bit. Okay, so you see the difference here, right? In the first case, keeping three singular values and tossing out one, we keep 97% of the matrix data variance, and the image that results is actually pretty accurate. In fact, at a quick glance, if you just kind of blur your vision for a second or shake your head and look at it again, you'll see, that's pretty similar. It's not too far off. But as we progress here, we see that we get a less and less accurate thing, which is to be expected, considering that here you have tossed out literally all the singular values but one. You've only retained a single one. You're trying to build. You know what that is saying. In fact, you can see it in the image. You are trying to build that entire matrix out of a single vector, right? You have tossed out all of the other vectors in U, and you've kept only the first one, the one associated to S sub 1, and you are trying to build that entire image from that single vector. And look at that image. That image looks as if you took like the first thing and slid it, right? It looks like you took that first line and then slid it almost, right? It looks like that's what has been done here. Okay. Okay. Moving on. So Justin put a picture of himself as a kid here in his notes to show how image compression works for a matrix like this. So this is a 200 by 200 picture. So 200 by 200 picture, or 200 by 200 image. So then the matrix in question is a very, very large matrix, right? The matrix in question is a 200 by 200 matrix. So A is 200 by 200. So there are 200 singular values. Okay, not really amenable to doing this by hand, but of course MATLAB can handle this. So here's a few of them. So listing a few in decreasing order as always. So S sub 1 is 114.6751. S sub 2 is 23.1226. S sub 3 is 17.6162. And S sub 4 is 10.0497 and so on. Okay, so like I said, there's 200 of them, but you can see how they get small pretty quick. In fact, by like the 20th or 30th value, they're under 1 after that. Okay, so I think S sub 30 and higher are all less than or equal to 1. Okay. Okay, so that's how it is. So note, if we zero out S sub 101 to 200 and have a look at the image associated to A prime, then it looks very similar. So Justin has done this in the notes. If you go from page 6 to page 7, so page 6, then page 7 to compare. So if you go from page 6 to page 7, you can see page 6 is the original image. Page 7 is the image that that you've generated from your matrix A prime, obtained from this SVD product, where you have altered sigma to be sigma prime. You've tossed out the last 100 of the singular values, right? So you get 200 singular values total. Toss out the last 100 of them, okay, and you get an image that looks very similar. Okay, and so then he repeats this where he's preserved all 200 of the singular values, 100, 50, 20, 10, 5, and 1. Okay, so look at page 8. So page 8 is a great example of how this all works. Okay, so let's look over the results of page 8. So the 200 values one is where every singular value has been preserved, and so nothing has been changed. That is the original image. So on page 8, upper left image, that's the original image. The 100 values image is where you have tossed out half of the singular values. So you've tossed out the last half from S sub 101 to S sub 200. You've tossed out the last half of those things, zeroed them out in the matrix, recomputed your A to be A prime, and generated that image. You get something that looks really similar, right? Tossing out another 50, right? So you've tossed out all but the first 50. Okay, so S sub 1 through S sub 50 you have kept, and everything else you have zeroed out. Recomputing that matrix A prime, generating the image, you get something that again looks very similar, right? So it's only when we toss out everything but the first 20, right? So that is, we are zeroing out 180 singular values. The smallest 180 singular values get zeroed out. The first 20 get kept. It's only then that we start to see some noticeable artifacts, some noticeable things being introduced here that clearly show that we have image quality issues, right? So if I were, to ask you to quickly judge whether or not there's a reduction in image quality from the first three, well, in the first case is just the original image, but in the first two things we did, if I were to ask you to see whether or not, just by looking at it, if you could tell there's a reduction in image quality, almost every one of you would say no, right? There's not really a noticeable reduction in image quality for the first three. But for the fourth one, it is clear that there's some reduction in the quality of the image. Okay, it still very much would let you match itself with the first three images, you would definitely look at those and say, yep, it's same image or very similar image. It's just a little blurry, but it's noticeably of lower quality. So then going to 10 values, you see that it is even lower quality, but still retains, retains some of its form. You could definitely see that there's a pretty steep fall off after this, right? So going from 10 to 5 to 2 to 1, you can see like the total collapse in image quality. But one thing that I'll have you note again is that in this one value where you've only kept the largest singular value, you are essentially building that entire image from a single vector. Okay, and the way that you've done that is kind of apparent here, right? So the way that you've built that from a single vector is kind of apparent, and just look at that image, right? It does look like you've taken a thing and like sheared it in some way, right? So it looks like you have taken the image and somehow like sheared like a single slice of it. Okay, you can even, like I said, you can see how it looks. Okay, and so the summary of that is we can see that the rank 50 version is still quite good. It's only when we get to rank 20 that noticeable deterioration of the image quality starts to take place. And the beautiful thing about the final rank 1 version is that the entire image is constructed out of a single vertical vector whose values correspond to shades of gray. So each column is a multiple of that value, and you can see that easily, and that's true. Like if you look at the single value case, you can see that every single slice of that image is just a multiple of the one vector that you're building it out of. Okay. So then what is the image quality? I talked about image quality in an intuitive way, as in you have an original image in front of you, and then I give you a version of that image that is either refined, made to look better in some way, or made to look worse, and then I ask you, what's the image quality of this, like relative to the thing I started with? So, intuitively you understand what that is, but how can we define image quality mathematically? So definition of image quality. Okay, so image quality can be defined to be the proportion of variance preserved in the new image. All right. So this is the sum of the retained singular values divided by the sum of the squares of all the singular values. Sorry, sum of the squares of the retained singular values divided by the sum of the squares of all the singular values. So, for example, in the case in the previous example, where we preserved S sub 1 through S sub 50 and tossed, and I should say zeroed out the rest, the image quality is the sum of the squares of the first 50 singular values divided by the sum of the squares of all the singular values. And it turns out that this is 0.999769 here. So keeping only the first 50 singular values preserves 99.97% of the image quality. Okay. So intuitively, the idea is that this image that results is 99.97% as good as the original image. Um, but then what does that mean? Well, what's nice about that is we've tossed out all but 50 of the singular values, and we've kept 99.97% of the goodness of the image, right? So that is a pretty big data saving that we've done, right? If you just think naively about how much data is needed to store this, we have gotten rid of a ton of these things, right? If you had 200 singular values and you're able to get 99.97% as good of an image by tossing out all but 50 of them, that's pretty good. Okay, so there's a table that is listed on page 9 in the notes that goes over the number of singular values and how much the variance is preserved by each of them. So there's a table where all that's computed. And as he notes, he says this is interesting because it gives us a sense of how much variance we would need to preserve to keep a reasonable looking picture, albeit only for this particular example. Okay, so obviously, you change the image, you've changed the initial matrix, you have then changed the singular values associated to it. So you could have an image whose singular values are distributed more evenly, right? So that even tossing out a handful of singular values would lead to a much worse image. That can happen. Okay, but as you saw here in this image, the way that the singular values were distributed was not at all like that, right? So at S sub 30, even a little bit before that, you had singular values that were already less than 1. Okay, going in decreasing order. So this gives you an idea of what's going on. So it says, while 90% seems like a lot, in this case, the resulting picture, the final one, is not good at all. So you'd probably aim for 99.5% or more. So what he's saying there is that it is not clear just by looking at the image itself, or it's not clear from the quality percentage itself. That is the number as you just read it off. It is not at all clear that what you have is good. So, for instance, draw your attention to the rank 1 case, or the case where you've tossed out literally everything except the first singular value. The quality percentage there is 90%, according to this table. But it's really bad, right? Like 90% in that case is bad. So then what does this mean? Well, what this means is that you can't think of it strictly in terms of the numbers, where 90% seems like it's a good thing. But in this case, as you saw in the final picture, it's not good at all. Even though technically, just computing the quality percentage in that case, it's 90+%, almost 91% of the variance of the image is preserved in that last case, but the image is completely unrecognizable. You can't even tell that it's a person. So don't be fooled by those percentages thought of in the normal way. In fact, for us, what we think of as good probably needs to be greater than 99.5%. And so to see that, you can look at this table. So note, maybe I should say a warning here. Don't think in the usual way about the percentage. Note from the table on page 9. that we really need image quality greater than or equal to 99.5% for the image to be good enough. Obviously, this is loosely defined here, but I'm just thinking completely intuitively. If I just look at that list of pictures, we saw that the 100 and 200, or sorry, the 150 values case, that was nice. Both of those, just looking at them, we couldn't really tell a difference. But for the 20 values case, where we tossed everything but the first 20 singular values, that there was some noticeable degradation there. We considered that not good enough. But if you go down to the table on page 9, the keeping the first 20 case, that preserves, that's 99.7%. Okay, and so that was like just barely good enough. There was some blurriness there, but you could still definitely tell what it is that was going on. You could still definitely tell it was the same image. But less than that, even though you're still at above 99%, you get there's just a lot of blurring. So yeah, that's one warning, is that I'll say don't be fooled, I guess, by your normal way of thinking about these percentages. And so the data saving is the next thing. It's kind of the entire point of this. So data saving, i.e. the entire purpose of all this. Okay, so what's the idea? So in this section, he says, yeah, it's important that we address, why we're doing this at all. So here we'll look at n by n square images. Images which are not square take a little tweaking and are addressed in the exercises. So I'll talk about that later. If we wish to save a grayscale n by n image in a matrix A using one value per pixel, then we need to save n squared values. Suppose instead we use the SVD and preserve k less than n singular values. So I'm going to write this out. So for a grayscale n by n image, we need to save, so this is A, we'll say A is an n by n. So for a grayscale n by n image, we need to save n times n, or n squared values. Okay, so suppose instead we use the SVD and save k strictly less than n singular values. Okay. So then we recalculate A prime as follows. So we have A1 prime, I compute from these singular values as S sub 1, V11, U sub 1, plus S sub 2, V12, U2, and so on. So this is how we built A prime with our, so we only go up to S sub k, that's the point. Okay, and then I do this repeatedly up to A sub n. So this is S sub 1 V sub n1 U sub 1 plus S sub 2 V sub n2. These are entries in that matrix V that I never write out. And so on all the way out to S sub k V. There shouldn't be a bar here because these are entries of V. It's not columns. U sub k. All right. So we recalculate A prime in this way. So if we think of the right-hand side as linear combinations of the u sub I vectors, then all you really need to save are those u sub I vectors. And therefore there's n values each of those, so k times n values. The coefficients to find each of those a sub I prime vectors is k values, so that's a total of k times n values again. So we need to save 2kn values. So it turns out this means in total I need to save 2kn values. So that is compared to n squared values. Okay. All right. So this allows me to define another quantity. This is compression ratio. What is the compression ratio? This is 2kn divided by n squared. So it's the amount that I need to save using the singular value decomposition divided by the amount I would need to save if I was just naively, literally saving every single entry in my original matrix A associated to that image. So then this is 2k over n. This is my compression ratio. And the way to think about this is that this is basically the thing that tells me whether or not I've saved space or how much space I've saved. So if 2kn is strictly less than n squared, or if k is less than n over 2, we've saved space. Right. So going back to previous example, so in the previous example that was talked about, preserving 20 singular values. Right. So this was the kind of worst image that I was happy to keep. Okay, so there was some slight blurring there, but still you could very much make out the image, tell that it was the same as the original image. It was still nice enough, right? So preserving 20 singular values, we can store the image using 2kn, which was 2 times 20 times 200, right? It was originally a 200 by 200 matrix that I needed. So I can store the image using 2kn, which is 2 times 20 times 200, which is 8,000. So that's 8,000 values. Instead of the n squared, which is 200 squared, or this is 40,000 values, i.e. the compression ratio is 8,000 over 40,000, which is 0.20 or 20%. Okay. Now keep in mind what that means. So the compression ratio is saying that this 8,000 is 20% of the total 40,000. So this doesn't say that I've compressed it 20%. It means that I've compressed it 80%. Speaking of it, using the verb compressed like that. The idea is that the amount of space I need is 20% of the original requirement. So whatever data requirements I have to store 40,000 values, I only need 20% of that. Okay, similarly, preserving 50 values, we get a compression ratio of, so saving 50 values, computing 2kn. So this is 2kn over n squared. So this is 2kn is 2 times 50 times 200 over 40,000. So this is 20,000 over 40,000. So 50%. Okay. Why is that important? So compression ratio of 50% means I have saved half the space. But recall, go back to page 8 for a second. The 50 value image was essentially the same. You couldn't really even tell a difference between those images. So you have, by losing almost nothing in terms of image quality, you have you have saved 50% of the amount of data needed, right? So you have literally taken up half the data that you would have normally. Okay, so the last section in this chapter, as all these other sections do, end with a description of how to implement this in MATLAB. So I'll let you guys read over that. Okay, so that's it for now. I'm going to go over, I'll have a similar lecture going over the chapter 12 stuff, and looking forward, as I said, the goal is that by the end of the course we'll have finished through chapter 15, so that everything except the optional chapters listed in the online notes list. And so I should have one extra lecture to talk about some fun stuff as promised at the beginning of the semester. So that's the goal looking forward. I'm going to post some problem sets later for all of you that won't be due till the end of the semester. So I don't plan on getting grades in any earlier than like May 17th. So we'll say May 17th-ish is when the stuff is due. Of course, you can turn it in whenever you finish it. But the problem sets will be additional warm up, for what's going to be the final exam, which is going to be similar to the online midterm that was given. So anyway, that's the plan going forward. So I'll see you all on Thursday.